talk about neural networks in sensors today. Sorry, this is, yep. Yeah, we're KONUX, so we're a startup from Munich, and what we do is we develop intelligent sensor systems. So really the whole vertical approach from hardware to measurement principles to simple data analytics all the way to long-term predictive maintenance in the cloud. And we come from an industry which is quite old, so a lot of signal processing happening in the industrial sensor world is still being done with conventional models, and we are kind of trying to break through these conventions by using machine learning models in any kind of signal processing task that we might face. And we learned that it actually makes a lot of sense, and I'm going to try to show you why in particular we use neural networks as compared to other models which are out there. So first, why neural networks? Then I'm going to show you an example where we use it basically on the bottom layer to find measurement principles inside sensor hardware, and where we are actually able to solve certain sensor signal processing problems which have not been solved for many, many years, and we were able to solve them with very simple machine learning models. Second, after that, once we get our results out of the sensor, we have to kind of classify and see, okay, is this something that is useful or is it not useful? So it's a typical classification task. Then predictive maintenance, so basically you get a lot of outputs which are kind of noisy, and over the long term you're trying to find out certain trends, and then you're finally able to predict, okay, this system that I'm looking at is going to fail in, let's say, 3.7 weeks. All right, so why neural networks? Mainly for three reasons. There's a hybrid character that neurons naturally give you. So you have the on-off gating character, which is particularly interesting for us when we work with physical signals over multiple ranges of measurement. And then, of course, you still have the perfect linear region in the activation function. And so, for example, what you see here is data from one of our sensors, and you see many, many different axes of different accelerometers. So we implemented an accelerometer for up to 100 G, because we know that our system has to be able to capture that, because it can get this high. But then, of course, as you can see, this is kind of a sudden movement, okay? And once it swings out, you can see that the red sensor only gives you noise, so you're not really able to use it anymore. But then suddenly the 2G or the 4G or the 16G, the lower G sensors kick in basically, so you're handling different sensors, which at the beginning, for example, you can see that the 24G sensor is capped, right? So it's saturated. Now, trying to find a formula as a human yourself, how it was done for the last, well, decades or hundreds of years in sensor technology, it's quite a tedious task. But as a sensor developer, of course, what we always have is training data. We have test benches with very precise, very expensive reference units. And so here it was actually about measuring acceleration for a short time and then translating this to movement in space. So everyone knows the very simple formula from school, how this would normally be done, but then of course once you go into real signals with noise and so on, you get drifts which completely destroy your whole signal and so on. And yeah, and we found that neural networks are really good for this. Second, the flexibility. Which you have by saying, okay, once I'm saying, for example, I have a customer who uses this sensor, but now I know that this customer is going to have an environment where you have a lot of temperature changes. And of course, because we're using MEMS sensors in the sensor of the left case, we know that they react heavily differently to temperature changes. So what do? We integrate a temperature sensor and we feed it as an additional input into our model. Of course, you can also do this with Gaussian processes, support vector machines, you name it. But it feels more intuitive for us during the development when you do it with neural networks, because it's really just like one more additional input to your intelligence. And also this whole topic of whenever we talk to customers and we tell them we're going to use neural networks, they're a bit scared because they think, okay, we're going to have some kind of a black box handling our data and we're never going to know for sure what is going to happen. Yeah? But we actually found that it's actually very much possible to predict the quality of your output. Yeah? It's never going to do anything crazy. We even found out that this is still true in sensors where you have really noisy data and you have no other signal processing other than neural networks. You can definitely make sure through regularization, through dropout during training and so on, to make sure that, yes, it is a black box that's doing something which you don't understand anymore as a human, but it's still predictable what kind of output quality you're going to have. And then one of the most important ones is the whole process. Yeah? There are many, many tools out there with which you can not only develop neural networks and train them, but also deploy them very quickly. So for example, when you use the MATLAB neural network toolbox as one example, you can immediately export it to C code. We can immediately put it into a tiny 200 megahertz microcontroller inside a sensor, and that's it. No more development, no extra overhead. And of course, neural networks are not only being used in classification, they're also being used in curve fitting, they're being used in time series problems. They're used in many, many different fields. So whenever we learn something about a new activation function, a new optimizer, a new regularizer, this learning applies to basically all our signal processing cases, which would not be the case if, for example, we used support vector machines, because then using them for very typical time series problems, kind of you learn something in one field, you cannot apply it to another field. And of course, we're using neural networks down on the C code embedded controller level, all the way up to Python in a cloud. Why ML in general? A bit more general advantages of using machine learning in a sensor startup. It's basically that, first of all, you're way more optimistic about what you do. Because before you had different tasks, certain tasks in sensor measurement principles, which you were not able to solve with classic formulas, and now it's actually possible. So someone telling me during the development, this is probably not possible, no, train a model and see if it's maybe actually possible. The agility that you have, kind of links to the adaptability. Of course, when you have a conventional model which you developed, it's very fixed. Of course, you might still be able to calibrate it within a certain space, but as I mentioned with the temperature adding case, or let's say you have another customer where you use it in heavy vibration environments, which for us is very often the case. You need to add some vibration measurement, you need to compensate for the vibrations, and it's done. But if a human would have developed a certain measurement principle formula, and you would tell him, okay, now adapt it for temperature compensation, first of all, he would think, oh, now I have to change my baby, which I developed over 3 years, and so on. So you are facing a lot of weird barriers, basically. And then, of course, the cost. I mean, it's a pretty clear point. We've been able to find measurement principle formulas through neural networks in basically a heartbeat, where other companies spend years and years on it. So measurement principles. One example. Now that I'm just going to give you a couple of examples what we do actually. So high-dimensional regression. What you see here is one of our torque sensors. For some of you who don't know what torque is, basically you apply a force here, the other end is fixed, and then you have a metal shaft. Even when it's turning very quickly, you will have some reversible twist inside the metal shaft. So you're measuring through an optical measurement principle, you're measuring the angle at the beginning and the end of the shaft. And then you subtract both angles and you have a unit which is linearly proportional to the torque that you want to measure, to the force that you want to measure. Okay, what we got here from our measurement principle which we developed, which we just kind of thought of, is basically a line of 60 pixels, and over 360 degrees you're scanning one revolution of the sensor. So now you know I get these slices of 60 pixels and I have to relate them to something that looks like this, okay, from 0 to 360 degrees, and again and again. So when it turns, you would get this kind of signal. So translating this to this, yeah, okay, not an easy task without machine learning. Of course, with machine learning, it's just a simple curve fitting task. What we used here is a 2 hidden layer, simple feed-forward neural network with 24 neurons in each hidden layer, 60 inputs, and the only pre-processing that was being done on the microcontroller in the sensor was moving average filter, and that's it. And yeah, and the training, of course, was being done offline, and then once the model is done, you convert it to C code, you upload it into the tiny microcontroller there, and that's it. Oh yeah, and one more important point here is that imagine you produce 1,000 sensors. Every sensor will give you a slightly different pattern. But before, our competitors, basically, they have to throw away maybe 50 of these 1,000 sensors because they were produced so poorly, of course still very precise, but still so poorly that their optical measurement principle, which is a fixed formula and which can only be calibrated in a narrow space, it didn't work anymore. But here, one time I actually took a sensor of us. It was only designed for 100 millinewton meter. I actually kind of broke it. The model didn't work anymore, but it was still kind of intact, and I relearned the network, and the output was fine again. Yeah. This is an advantage which other measurement principles don't have. Okay, the next example goes more in the direction of time series. What you see here is for one of our customers, we have a movement sensor. So this is what I mentioned before. You have tons of acceleration data of different ranges with different noise patterns. And what you're trying to predict is what you see here. Basically what happened here, this thing is attached to something where something else basically moves by, and you're always trying to measure how much it moved when the thing moved by. And what you can see here, the blue line was measured through an actual laser distance sensor, so very precise, and the red one is the output of our model. And it's very stable, even over a couple of seconds, it never drifts away. So this is something like, for some of you who may know it, taking acceleration and predicting the movement in space over a couple of seconds for a long time, it was thought of impossible, especially with very cheap MEMS sensors, which we use for $2 maybe. Here you see the difference between the two. So the prediction was precise up to, at worst, 0.4 millimeter. And here down there, you could actually see that then through some more post-processing, which is very cheap, you can do things like counting how many times the thing that moved by. Yeah. You were noticing maybe that I'm not really allowed to say what it is, but yeah, it's kind of a vehicle. Okay, then once we captured basically the times when the vehicles move by, so you can see here the first six red data captures of acceleration. This is just the raw acceleration signal. This was actually the thing that we wanted to detect. And here, with the same offset, we have random movements. So this could be rain on the sensor, it could be someone walking by, it could be a truck driving by, something that we actually do not want to detect. But it would still, of course, give us an output in our model. But before actually uploading it to the cloud on the sensor, we want to be able to predict, okay, is this really something that we want to upload or not? And so I manually generated some training data. So here you can see a very simple model with just 2 hidden layers and 3 neurons each in an ArcSnet with a 15-tab buffer in front. It was able to very nicely say, okay, here there's a 0% probability almost that this is the actual vehicle that we want to detect, and here for all the others, it detected it very nicely. And then finally, once we have our results over long term, we looked at this system for weeks, months, years. What we want to do is predictive maintenance. So some of you may know this term. It's basically about predicting when a machine has to be maintained before it actually has to be maintained, so that you save money because something doesn't suddenly fail and you're able to foresee it. The way we do this is mainly through anomaly detection. So what we do, we have a machine like this pump here, for example. We have a certain spider web of sensor nodes. We attach it. We combine all the different signals like ultrasound, microphone, acceleration or vibration, temperature, And then we create a model which represents the normal state, and then through anomaly detection, we are able to say, okay, now over time, this system changed so much or so quickly that it's an anomaly with this and this probability, and yeah. All right, and my time is over, and thank you. We're looking for talented developers, so if you're interested, please contact me. Thank you.